So for circular cylinders now, which is the next topic, we'll be looking at some examples here very quickly. But very similar idea. You know, I have this rod. I'm going to apply torsion to this rod, and again, I'm going to try to determine what is going on, what is the shear stress that's caused by this torque applied. I already covered the formulas for that. I already did it for you guys. We covered that already in just the lecture previously to just right now. But I want to cover it into more details a bit more. The formula for this, and I'm not going to go through these assumptions again. They're the same assumptions I used for Saint-Venant's principle, but we already reviewed this. You know, tau max is equal to twice the torque applied divided by pi a cubed. So we covered that. A is the radius, and this is equal to ma over j. So that's another formula you can use to get the answers to the problem. That's at the outer fiber of the rod. Or if you want to look at some other point internal to the cylinder, then it will be m times the radius divided by j, where j is the polar moment of inertia, pi a to the fourth divided by 2. And by the way, you can plug pi to the a to the fourth divided by 2 into this formula, and you will see that you'll get the formula here is exact same formula I showed you earlier on when we covered it, when I derived it using Saint-Venant's theory. Then you can calculate shear strain using this formula, actually, because if I know shear stress, then I know the shear strain. So that's going to be this divided by G. So AMR divided by JG. G is a shear modulus, J is a polar moment of inertia, M is a torque that you apply. And the angle of twist can be easily solved, and you'll get the total angle of twist will be phi equals the torque applied. I change this from moment to torque to be consistent with a lot of books you find out there. L is the length of the rod. G is a shear modulus. J is the polar moment of inertia. So here's the max shear stress, and here's the angle of twist. Yeah, this phi is not the Prandtl stress function. I'm trying to use the convention people use in different books, and they use phi a lot. So I apologize for that, for switching that on you. But Prandtl stress function was phi before, but while now we're using a different convention. Example number 1, statically indeterminate problem. The problem statement is giving you is asking you to determine the lengths A and B if you want to keep the shear stress the same across this boundary. So it's telling, hey, I want the shear stress to be the same across this boundary. It's a statically indeterminate problem. Torque is applied here, and you don't know what the torques are at either end. The diameters for section A and B are given to you, and we want to solve this problem. So this is a circular shaft. And like I said before, I like to write the problem statement in what's given and what I want to find. I want to find the lengths A and B such that the shear stress is the same across the boundary. That's what this is asking you to do. So all you have to do is do a free body diagram. The free body diagram tells you that the torque at this end should be torque A, and this should be torque B. And at the center where the torque is applied, not center, but at point C, we apply a torque T. So torque has to be equal, this torque here that I apply has to be equal to the torque A plus torque B. That has to be true by equilibrium. By compatibility, you need to have the angle of twist at this particular point to be the same, coming from this side and coming from this side. There's just no other way. The phi has to be the same, otherwise the thing is broken. So the phis have to be compatible at this point. So for that reason, I know what phi A is in terms of torque A, and I know what phi B is in terms of torque B. So I know that length is A, so I'm using the twist formula, which was torque times length divided by J times G, the shear modulus. So very easy then. I have to just equate this to that. And when I equate this to that, that's what I get. And then you can take this equation and this equation and solve them together. And when you do, you can solve it in terms of torque A, this torque A here, and you can solve it in terms of torque B here. And now I was able to take care of the indeterminate aspect of the problem. I was able to take care of that. I can then introduce, use the shear relationship. Remember, the shear stress is given by this formula. I can use that formula. Remember, I'm using torque T instead of M, but it's the same formula as this one. I'm using radius here, I'll be using diameter. So diameter divided by 2. So you're going to see that there, diameter divided by 2, right there. And these two need to be equal at that point, at this point here, because that's what the problem statement states. So we make that equal, and we also know that this is equal to that. So, sorry, this is equal to that, and this is equal to that. So with these two formulas, you can actually show that A over B equals D over A, dA divided by dB. So the ratio of the lengths A over B are equal to the lengths of the ratios of the diameters. So I'll let you check that out home. Pause the video there, just check it out home and try it yourself. The length is A plus B. Obviously the whole length going from the left side all the way to the right side. And so now all you have to do is solve for A and B, because you know that the A over B is this, and you know that length is A plus B. So you can solve for A and you can solve for B. It's just equations. You know all these values. You know the diameter, you know the length. So plug it in and it gives you the value of A and B such that the shear stress at that point is equal. And so that's how this problem was done. Problem number 2, we want to look at maximum torque applied to this problem. Here in this problem, they're giving you a maximum shear stress allowable of 70 megapascals, and they want you to find the torque T. Very similar problem setup. They're giving you the diameters and the lengths now. So now the lengths are known to you. And now the only thing that's given to you is the shear allowable. So you don't want to exceed that. Find the torque that you can actually survive. And if you want to design something that survives, you increase the diameter if it's going to break. So you can find solutions to the problem. Same equations. Torque A plus torque B has to be the torque in the middle. And by compatibility, the same thing needs to be the same there. So the phis are the same in the center in terms of torque A and torque B. And you can solve simultaneously like I did in the previous problem. So that stays the same as I had shown before. And now I can solve for torque A. You can see that there. I know all the values here. I know all these values here. They're given to me in this case. So torque A can be solved completely, and I get 0.8283 torque T. And then I can solve torque B very easily, because that's just using this equation here. So I get torque B. And now I can calculate the max shear stress in the portion A, which is, again, torque times the radius divided by J, or diameter divided by 2, doesn't matter. When you plug in all these numbers in, this tau has to be no greater than 70. It cannot be greater than 70. So you can find the torque that goes with that. That's 259. And then for the section CB, the next section, you can then also do the same thing, and you get a torque of 270. In design, you obviously want 259, because if you apply 270, then this one breaks. So you want to make sure you design to the lowest value of torque so that the whole assembly survives. For a narrow geometry, you can also analyze it. I'll cover that in the next example. So torque of a rectangular rod. Here I have a rod that has 2 different cross sections. And I want to calculate the maximum permissible applied torque and the corresponding angle of twist. And this is just using that table I showed you earlier. So in this case, they give you all the dimensions you need, even the shear modulus, and they say that the allowable shear stress is this. And they also tell you what the angle of twist is even. So they're telling you, hey, what is the max torque I can apply to this system? In this case, I'm not applying a torque in the center. I'm applying on the edges. And they're asking, hey, what is the corresponding angle of twist between the 2 sections? So right here, what's the angle of twist there? So that's actually a very easy problem. All you have to do is to look at the cross section for section 1 and then for section 2. And when you do that, you'll find that A1 over B is 2 and A2 over B is 1.5. Then you can go into these tables and figure out what the formulas are, what the different constants are. So A over B in one of the cases 1.5 as an example. So beta is 0.196. That beta goes here. You know A and B for the problem, so you know this relationship. Also, it tells you what alpha needs to be, so then you know that number as well. So then you know how tau relates to torque according to this equation. So everything's provided to you, and so you can solve for the minimum torque based on the first formula and the second formula. So based on the first formula, I get 468. Based on the second formula, I get 499 because I know the theta allowable. They told you they cannot exceed 1.5 degrees. I put it in radians here. So the maximum torque allowable should be the least of the two, which is 468. There you go. That's the max torque allowable. To calculate what's the angle of twist, you can do the calculation. It's the same formula I showed you before, which is phi equals T, the torque, times the length divided by GJ. And J here is given by B cubed beta 1 times A1 for section 1, and it's B cubed times beta 2 times A2. Again, this is a very straightforward calculation because now you can add the twists to get the total twist. And the total twist is 4.37 degrees. So I went really fast to example 3, but the good news, this will be recorded and you can pause it and do it yourself. And you do have questions, please email me and we'll take care of that. With that said,